Okay, so we left off part 1 of 2-2 notes by looking at the average velocity based on a vertical displacement versus horizontal displacement graph. And again, the big thing I want you to be comfortable with here is this is just saying if I want to find my average velocity vector, well, I know in order to find my actual vector, I would just have to find my x component and my y component, right? Well, the way that I can find my x and my y component based on this graph would be to find my change in x over change in time and my change in y over change in time. The only thing that is tricky about this, right, the only thing that's tricky about this particular graph is I don't have any reference of time on it, right? So the time would have to be given in addition to this graph if I actually wanted to find my velocity. Now in this case, I can find the direction of the velocity because I would know that from point 1 to point 2 it goes a certain rise and it goes a certain run, right? So I'd be able to figure out the direction of my velocity vector at that average time interval there. But I wouldn't actually be able to solve it unless they gave me the time over which that happens. So I wouldn't know the magnitude of that velocity. Maybe it's longer, maybe it's shorter, maybe it's way longer than that. I just don't know. But anyway, getting comfortable with a vertical displacement versus horizontal displacement graph. That's definitely something we'll look into doing. Okay, so the question then is, what happens if I ask you about the instantaneous velocity? Well, just before we even get into this mess, because I know it looks intimidating, but before we do that, let's just go back to our original, right, position versus time graphs. We said on a position versus time graph, if I asked you to find the instantaneous velocity at, say, this point, well, we know that the instantaneous velocity would be the tangent line, the derivative, or right, the slope of the tangent line there. In order to find that, what we did was we first kind of approximated that as secant lines that were getting closer and closer to that point, right? So that's all this graph is really illustrating down here is the direction of the velocity would be the direction of the tangent to that curve, right? Again, I wouldn't know the magnitude unless I knew the time. But anyway, so when I look at this equation, again, it looks intimidating, it looks like there's a whole lot of stuff going on, but notice here it says the limit as delta t approaches 0. Well, what that actually means for me is, again, on a curve, if I want to find the instantaneous velocity at this point, I want to know basically what's the average as that time difference is very, very small. Because if I choose 2 points that are infinitely close together, I've essentially got 2 points on that tangent line, and that's really just the definition of the derivative for us, right? So all this is saying is if you want to find the instantaneous velocity based on a position, a horizontal and vertical displacement graph, I just need to do the derivative of my v of x function. So I need to do the derivative of that, and I need to do the derivative of my v of y function, right? Or the derivative of my position functions, I should say. Sorry, the derivative of my position functions to give me the velocity functions, right? So it's really the same type of thing we did for one dimension. So that, again, derivative of the position and the position, which would be my v of x function and my v of y function. But anyway, we'll see an example or two, so hopefully I clarified that mistake a little bit more. But all this is it's taking what we did all of last chapter, right? If I gave you a position function in terms of x of t, and I asked you to find the velocity, so if I gave you this and said this was 2t to the third power minus 2t, and asked you to find the velocity, well, you could just do the derivative, right? And then plug in the value you wanted to find the velocity at. If I've got two-dimensional motion, I do the exact same thing. I just do the derivative of each part individually, and I find the velocity function for each part individually. That's really all this equation is saying. It's just doing that in a rather intimidating way. But I do want you to be comfortable kind of looking at this and seeing that, right? Again, my instantaneous velocity would be the derivative of the position function for my v of x and the derivative of my y function here for v of y. So anyway, we'll see a few examples to hopefully illustrate that point a little bit more. But before we do, just to touch once again real quickly here on the difference, right? On a position versus time graph, the slope gives us the value of the velocity. So we know that the slope gives us the magnitude. I actually don't know based on a position versus time graph, so I know the magnitude of the accelerator or of the velocity here, right? It gives me the velocity's magnitude. I actually don't know the direction, right? If I look at this graph, I don't have any semblance of which way is the velocity going. Now I know it's positive, right? But that only tells me in one dimension. So when I have a position versus time graph, this is really just showing me one-dimensional motion. I know it's going in the positive direction for that one dimension, but what if there are two dimensions? This graph doesn't really illustrate two dimensions very well. The only way I could see two dimensions on this graph would be if I gave you a second graph to represent maybe the vertical displacement and one graph to represent the horizontal displacement. Okay, so this graph is a little bit limited in what they show me. The new graph that we're starting to work with here, so my y versus x displacement, is also a little bit limited because it shows me the direction of the velocity, but it doesn't tell me the magnitude of the velocity, right? Because this graph doesn't give me any semblance of time, I don't actually know what my velocity is, because while I know my direction for the changes, I don't know what I'm dividing that by, right? So this one tells me what direction the object is moving, but it doesn't tell me how strong the velocity actually is, whereas this one can tell me how strong the velocity is, but I don't necessarily have a full picture of the direction. So in a sense, these are both giving me glimpses of the motion, but neither one by itself tells me the entire motion, right? There's got to be more to it for me to figure out what this object is actually doing. But anyway, we'll get some practice with these graphs as we move into this section. And so this one right here actually gives us a pretty good chance to do that. So it says a particle's motion is described by two equations, and notice it simply gives me two different position functions, right? It's telling me there with that first function that the x position function is given by 2t squared, and then the y position function is given by 5t plus 5. They tell me for both of these t is in terms of seconds, which is good just to keep it in position. But anyway, draw a graph of the particle's trajectory. So when they ask us for the trajectory, they're asking us for the ball's actual motion, right? So when we see that term for trajectory, what that's asking me for is what is the vertical displacement versus the horizontal displacement, right? I'm looking for what is my position versus position graph, if you will. Okay, so in order to do that, probably the easiest thing we can do is just make an x, y, t table, right? So what I mean by that is truly going to have my x value, I'm going to have my y value, and then I'm going to have my t value. So whether you want to put that in front or behind it doesn't really matter. Maybe I'll just throw it out in front for us, right? But if I know both of these functions in terms of time, then I can find out where the x position would be after a certain amount of time, and I can find out where the y position would be by just plugging in that time. Right? So if I plug in 0, for instance, well, the x position would be 2 times 0 squared, so just 0. Whereas the y position would be 5 times 0 plus 5, so it'd be 5. If I plug in 1 second, well, after 1 second, my x position is now 2 times 1 squared, so 2. And my y is just going to increase linearly by 5, right? So it'd be 5 times 1, which is 5, plus 5, which is 10. Right? So we'll notice here that this just is a linear equation, so this one just goes up constantly by 5. If I plug in 2, I do square that first, so it'd be 2 squared, which is 4, but then times another 2, which is 8. And then y goes up by 5. 3, which would be 9 times 2, so 18. And once again going up by 5 here. So you could continue this as far and as long as you needed to. I'll maybe do one more point here just to illustrate the next point, and then we'll start to graph this. Right, so we got 4, this would be 16 times 2, so 32, and then 25. Okay, so if I want to graph my position, my trajectory, right, all I'm going to do then is plot these points. Okay, so here's my vertical displacement, here's my horizontal displacement. My vertical displacement's going up by 5s, my horizontal is going up randomly, right, it goes up by a little bit more each time. Not randomly, but it goes up by more and more each time. Right, so I'll maybe just scale this by 5 so I can get a good clear picture of what's happening here. So 5 meters all the way up here to 25. And then go over by 5s as well, just to keep a nice even scale for us, so we can get a feel for what this is actually doing through space as it moves. And I don't mean space like outer space, I just mean like physical space, right? But anyway, so it started at 0, 0, 5, so it actually started up here from 5 meters. So maybe this was thrown off of a very short ladder, probably not a building, right? Because it'd be a pretty short building to be 5 meters tall, but it'd be a pretty tall person to be 5 meters tall too. So anyway, it's thrown from a step stool perhaps, right? And then over time, right, after 1 second, and keep in mind I don't have an axis for 1 second, but after 1 second I know it'd be at 2, 10, right? So I know that the ball would be at 2, 10 1 second later. After 2 seconds, it'd be at 8, 15. So again, over here, obviously these aren't going to be perfect because my scale is not perfect here, but it's going to be close enough to give me a pretty good feel for what's actually happening. After 3 seconds, it's 18, 20. So it'd be way over here-ish. And then after 4 seconds, it's all the way over at 32, and then 25. So what I do clearly see, I hope, is the fact that this would have a curvature to it, right? So there's my actual trajectory. There's the actual path that this ball would take as I threw it through the air. So again, this actually shows me, if I was looking at a side view of this, so if I'm standing here and throwing the ball and you guys are watching it from a portrait perspective here, then you would actually see the ball at these locations after 1, 2, 3, and 4 seconds. So it actually does help us visualize what the ball is doing, but the problem is it doesn't necessarily tell me, right, anything about the velocity's magnitude, at least not directly. Now if I bring the time in, we can find that. Okay, but anyway, so we've done that for part A, so hopefully part A wasn't too bad, right? For part B, you basically do the same type of thing, except because it wants the speed as a function of time, I need to figure out my vertical and horizontal velocity functions. Okay, so all we're going to do for this is we're going to take those two functions and we're going to find our velocity functions that go with them, right? So basically I'm just going to find the derivative of them. So my x position function was 2t squared. My velocity function would be 4t, right? Just doing the derivative. My position function for y was 5t plus 5. And then so my derivative of this, and notice I dropped the parentheses just to keep it simpler for myself, right? But the derivative of this would then just be 5. So what that tells me is, and I'm sorry, this would be my y velocity. But what that tells me is my velocity, my vertical velocity, is actually constant at 5 meters per second, right? Whereas the x velocity is going to depend on how long it's been in flight. So this is an interesting case where we actually see a horizontal acceleration, but a constant vertical velocity, so we don't have any vertical acceleration. But anyway, now that I've got those two functions, if I want to find my speed versus time graph, so I want to make really a velocity versus time, except I just want the speed, so I don't care about the direction. So I'm making a speed versus time graph. But in order to do that, right, well, to find the speed, I would find the two components and then do the Pythagorean theorem. So this time I'm actually going to make myself a t, vx, vy, and then what I'll just call v, but this is just representing the magnitude, just the speed table. Okay, so it's going to look kind of busy at first, but the reason I'm going to do this, I need to know my horizontal and my vertical components in order to find the actual magnitude of my velocity, the speed of my velocity there. Okay, so after 0 seconds, right, after 0 seconds, we're plugging in 0 to my velocity function would just be 0. Plugging in 0 to my vertical function, well, there's nowhere to plug it in, so this is just going to be 5. And in fact, obviously, that's going to be 5 all the way down. Well, if one component is 0 and the other component is 5, then the resultant, right, the magnitude of the resultant here would be 5 as well. So what that tells me is that 0 seconds, my total speed was 5 meters per second. Again, I actually know the direction, but I don't care about the direction. After 1 second, well, after 1 second, my horizontal velocity is now 4, but my vertical velocity is still 5, right? So after 1 second, if I want to find the actual speed, well, again, just all I'm doing here is the Pythagorean theorem. I would do 4 squared plus 5 squared and then the square root of that, and I'd get about 6.40, right? So I'll call that about 6.4 meters per second. After 2 seconds, do the same thing. This is now 8, this is now 5. If you do Pythagorean theorem for that, you get about 9.43. And then for 3 seconds and so on and so forth here, this would be 12, this would be 5. That's actually a nice Pythagorean triple. So this would be 13 meters per second, right? And you could keep going. At this point, I've got a few pieces of data, so I may go ahead and stop here and graph it, just so I have enough time to get this plotted here for you. But in any case, I don't actually care about these components, right? These components just help me find the final speed of my particle. So at 0 seconds, I know the speed is 5, and then I work my way up to about 13. So I'm just going to go up maybe by 5s. So 5, 10, 15. 0 seconds, the initial velocity, the initial speed, the magnitude of velocity is 5. After 1 second, it's up to about 6.4. After 2 seconds, it's up to about 9.43, so close to 10. And then after 3 seconds, it's up here at 12. Okay, so we can see kind of that speed progressing as we do that. Anyway, just getting comfortable. I'm not real worried right now about looking at the curve. We'll look more at that as we go, but getting comfortable plotting these graphs based on data.